Welcome back, everybody. Let's continue where we stopped last time. So last time I managed to tell you all of this without mentioning cluster algebras. So we cannot go on forever like that. I'm afraid I have to introduce cluster algebras. I know Sylvester told me he kind of reminded you what there are in his TA session, but I'll quickly remind you again. So what is we'll start with a keyword. So everybody can hear me. Everything's okay. Shall I keep going here?
Yes.
Yes.
Okay, so we start with a keyword, which is just a fancy word for directed graph. And then when we mutate at the vertex, we can mutate this graph itself, this keyword, at vertex z. We do the following. First, for each pair of edges, x going to z and z going to y, right? Those are directed edges. Create edge x going to y. Then reverse all edges adjacent to z, and then cancel all two cycles. Okay, let's do an example. Again, I suspect you've seen it, but let's just do an example. Let's start with this keyword over here. Oriented so that there's little oriented squares. And now let's say I want to mutate it at this vertex over here. Maybe I'll give them names like 1, 2, 3, 4, 5, 6. So just as names of vertices. Okay, so I want to mutate at vertex 2. What happens? There is this pair of edges going through 2, and there is this pair of edges going through 2, right? There's two pairs like this. One incoming, one outgoing. For each of them, I need to create a direct edge. Here, I create direct edge from 5 to 1, and I create a direct edge from 5 to 3. Then I reverse direction on all edges adjacent to 2. So I'm mutating at 2 over here, right? So I reverse direction at all edges adjacent to 2. So now those arrows point the other way. And then if there were any 2 cycles, I would remove them. There is no 2 cycles. Everything else stays the same. We get this period. Let's do it one more time. Or maybe let's do it 2 more times. Let's mutate at vertices 4 and 6. Well, let's just do 4. If we do it at vertex 4, what happens here? We have one sequence of edges going like this through 4. So we have to create one direct edge from 1 to 5. We create this edge. We reverse edges at 4. Everything else stays the same, which by and except we need to remove the 2 cycles, which in this case, there is a 2 cycle over here, so we just remove it. Okay, and then if you do it one more time at vertex 6, we will get something which looks like this, right? So let's see. Okay, which is almost the same QR we started with, except all arrows are in the opposite direction. Okay, so far so good. That's pure mutation for you. So there was only one step at which we had this two cycle thing. Oh, actually there were two. There was also two cycles at this step, right? When we mutated 6, we create arrow this way, which cancels out arrows that way. Okay, this is an example. And now there's also, this is just how the keyword changes. And now there's also mutation at variable. So what happens is at the very beginning, we plant a variable, which could be just a number or some formal expression in some field at each vertex. So and the rule for variable mutation is like this: mutation variables. The rule is like this: if you mutate at vertex I, then the old value xi times the new value, which is xi prime, let's denote it xi prime, is equal to sum of two monomials. First one is product of all arrows going out of I, whatever stands on the other end of the arrow. And the other one is product over all arrows coming into I. Product of whatever stands on the other end of the arrow. So for example, if we here started with variables x1, x2, x3, x4, x5, x6, what happens, first mutation, we are mutating at vertex 2, which means all other variables stay the same, x1, x4, x5, x6, x3 stays the same, and the x2 gets replaced. And what it gets replaced with in this example is, let's see, outgoing arrows, x1 and x3, incoming arrows, x5, and you divide by the old value. And that's your new value. Yeah. So this is a bizarre definition. If it's like the first time you see it, it's hard to believe that somebody would care about it. Like it's not obvious. Like, why is this even natural? This is a strange procedure where you keep changing your graph, and you keep somehow changing things which sit at the vertices of this graph. And why would it be natural? Why would anybody care about it? So the reason is that it arises naturally in many, many contexts. But to believe it, you need to see it that it does arise naturally. So right, so you start believing in cluster algebra sort of once you start seeing that they do somehow come up in nature. And by nature, I mean mathematics, like other areas of mathematics. Okay, any quick question, especially from people who haven't seen this before. If you haven't seen this definition before, it's a little weird. You have a graph. You're allowed basically. You imagine that like you click on one vertex and the graph changes, and also the thing sitting at this vertex, the number or the variable, whatever the expression sitting there, also changes. And you just keep clicking. You can choose where to click next, and that's how you mutate your keyword, and you mutate variables associated with it. So any quick questions about this? Right. So for example, when we mutated x4, what was x4 prime over here? Let's do small exercise. What was x4 prime?
You mean when we mutate at the... Ah, I see what. Yeah, if it was a prime, yeah.
So when we go from this,
It's x1 plus x5 divided by x4.
yeah, x1 plus x5 divided by x4. But okay, so but now one thing you can recognize is that the stuff we were doing yesterday is actually a special case of this. So if we take one of our Denking diagram, or more generally bipartite graph, and we orient all edges from, say, white to black, well, then how do those exchanges work? What would the rule tell us? It will tell us that x2 prime is equal to, well, we divide by x2, incoming arrows x1, x3, outgoing arrows empty. Empty product is 1. So plus 1. And that's exactly what we were doing yesterday, right? So, oh, not yesterday, last time. So what you can see here, and by the way, and quiver changes also correctly. So what you can convince yourself is that if you take your bipartite graph, for example, a path graph, right? So I don't know, or one of those other linking diagrams, or any bipartite graph, and you orient it in this manner where it's every arrow is white to black, and then you start say you mutated all black vertices. What will happen? Well, there is no new path to create. There's no passes going through it because there's no outgoing arrows. So there's the only thing which happened is you reverse direction of all arrows. So after mutating at every black vertex, the new quiver will look like same quiver, just all arrows are reversed. And then you mutated all white vertices and you get back the original quiver. So and the dynamics of variables at vertices is exactly what we wrote last time, right? Every time they change exactly according to the rule for those T systems we wrote last time. Okay, so at least we can recognize that for this very specific kind of quiver where it's bipartite and all edges are directed from one side to the other, this cluster dynamics, and we keep doing, black, white, is exactly those T systems we were looking at last time. Any questions about this? Now, this guy I showed you at the beginning today, he was kind of special. Remember, I showed you this quiver. This quiver is bipartite in the sense that we can color all vertices black and white. Right, so all edges connect black to white. But it is not of the type I just told you. Like, not all edges go black to white, right? So some edges go black to white and some edges go white to black. But what we checked is that if you mutated all black vertices, you get the same quiver, but with all arrows reversed. Right? We checked it. Hopefully, I mean, if you were taking notes, you should have it. So if you mutated all black vertices, so here, let me try to draw it again. So here's our vertices. If you mutated all black ones, we will get this guy. And then you mutated all white ones, and you get back the original one, which is still the same, but even the same orientation of arrows. And you can keep going like this. So in cluster world, as long as you keep getting back the original quiver, that's the setting when people would call it a T-system. So most general use of word T-system. So originally it was reserved for more special cases, but sort of more modern kind of most general use of T-system is a T-system is just a way to start with a keyword and click a bunch of stuff and get back the same keyword. Okay, so and that's interesting. People study this. People in integral system like to study this kind of thing. So and a lot of things again, lots of math which arise in nature are of this kind, where you start with some keyword, you click, and you get back the same keyword. Except the variables change, right? You get the same graph, but the variables change. Well, but since we get so there are two questions to ask here. Well, there are more than two. Okay, so first of all, not every keyword will be like that. Right? There will be some keywords, even bipartite keywords. Like if we try something here, let me give you an example. Okay, so let's try this keyword. If I click at my two black vertices, what will I get? Uh, well, the vertices stay the same, of course, but this one will create one arrow in this direction, but this one will create two arrows in the other direction. Does everybody see it? Because there are kind of two paths going this way, because there are two arrows here. Yeah, Sylvester, I'm recording it. That's fine. So if you mutate the two black vertices, you will get this at the end. Uh, One of them will cancel out, but the other one will not. So it's not a T-system. So here's our definition. If after clicking black or white, keyword stays the same up to reversal of all the arrows, right? So except all arrows globally gets reversed. We call such keyword recurrent. And we say that's associated, and we talk about associated bipartite T system, right? So it's a specific T system where you click on black, white, black, white. So we call it bipartite T system. Uh, okay, so far so good. Any questions about this? Don't be shy.
Yeah,
I really like questions. Please ask me.
I have a question.
Yeah,
Let's say in a graph that you wrote, this bipartite graph,
this
if
one
you
or this one?
no this one,
This one. Okay.
uh, yeah, if you say click on some black edge, you will get actually something like x1 plus x2 divided by something. But yesterday, not yesterday, but on a previous lecture, we defined the process to be multiplied by everything that's connected plus one divided by
Right. So this
vertex
is a more
itself.
general process. So
Okay.
if your quiver is such that all arrows go from black to white or from white to black, you will get what we had yesterday.
Okay.
The reason you are not getting the same thing here is that this is a more general kind of quiver where some edges go black to white, right? Black to white. And some go white to black. So what we did yesterday was a special case,
Okay.
right? Does it make sense?
Yeah, sure.
So,
Is
but
there any
but
rule?
okay, but now, well, any other questions?
Yes, I wanted to ask, is there any rule to how we set the directions of the edges?
At the moment, it's just a definition. So at the moment, we are just saying the following. Take any quiver which is bipartite, right? So any quiver where vertices can be divided into black and white such that all arrows connect black to white. So just bipartite as a graph. And allow yourself to just click all black vertices or click all white vertices. It's something you can convince yourself that because they're not connected to each other, it doesn't matter in which order you click them. Right, over here, I could have clicked this one first, then this one, or I could click this one first, then this one. Doesn't matter because they're not connected to each other, those two. So we take all black vertices, we click them, and we ask ourselves, did we get back the same keyword? If we did, we like it. We call it recurrent. We say that we associate to it a T-system. If we didn't, we don't like it. So you can orient anything any way you want. But once you orient it, you will try clicking all the black ones. And you will ask yourself, did I get back what I started with? And you will try clicking all the white ones. And you will ask yourself, did I get back what I started with? And if you do, that's one of the guys we want to look at. And if you don't, it's not one of the guys we want to look at. Does it make sense? So we allow ourselves any quiver like that. We just like some of them and we don't like some other of them.
Yeah, that's clear.
Say it again.
That's clear. Thank you.
Clear. Okay. Okay. So for example, this one doesn't work for us. It's not a recurrent quiver. But this one is a recurrent quiver. So we will study this one, but not study this one. Okay. So, no, but this was a good question. So far, I didn't give you any rule how to create them. I just said, if it has this nice property, we'll give it this name and we will want to study it. Okay. Any other questions?
And can we check whether it's a recurrent quiver or not by definition, but by some other, I don't know, other any?
Yes. So
Yes.
so okay, two things. First of all, checking by definition is not that hard, in the sense that just clicking on all white vertices, because they, order doesn't matter. So it's something reasonable to do. Is there any other way to check? So here's one way to think about it. Ah, how about I come back to it in a little bit? I will tell you the answer. So it's just something about adjacency matrix of this graph, okay? It's something about adjacency matrix of this graph, but I will tell you in a little bit what, because I need to say just one more thing before that.
Okay, and this mutation operation, it's commutative, right? On the vertices.
If the two vertices are not connected. So if I click here and then click here, I could have clicked first here and then here. But if I click at those two, it will matter. If I click here and then here, the result will not be the same as if I click here and then here.
Okay, so in general, it's not commutative.
In general,
Okay.
it's not. But because
Thanks.
our quiver, we are assuming it's bipartite. So all the black ones are not connected to each other, and all the white ones are not connected to each other. And for that reason, I can just say something like this: just click at all black vertices without worrying about in which order. So in general, not commuting, but in our special case, all the black ones will commute with each other, all the white ones will commute with each other. Okay, those are good questions. Anything else? Okay, so of course, the big question I'm trying to lead to is, can we play the same game we played last time? Last time we asked ourselves, when is the T-system? And by T-system, we don't just mean the graph, we mean the variables, right? It's how the variables change as we keep clicking. When is the T-system periodic? For example, this guy, we know this is a recurrent quiver. If we just keep clicking black, white, does it come back or does it not come back? Does the question make sense? Okay, let's try it. Okay, so let's just try it. Just like last time, except now the setting is slightly more general because we allow ourselves more general quivers. Our quivers now are not all oriented from black to white. They're kind of more mixed. So let's try. So I will just start with all ones and I will write it like this. Okay, so it just means that 1, 1, 1, 1, 1, 1. Okay, so that's okay. So first we mutate at those 3 ones which are black. What do we get? The first one is easy, right? It's just we got 2s there. Is everybody comfortable? Like, right? I mean, this guy becomes 1 times 1 plus 1 divided by 1, which is 2. This guy becomes 1 plus 1 divided by 1, which is 2. Okay, next step. So this was all black ones. Now let's do all white ones. So 2, 2, 2 stays the same. 2 plus 2 divided by 1 is 4. And then 4 plus 2 divided by 1 is 6. Okay. Do people follow this? Okay, I'll try to make a mistake and see if you can catch me. Okay, so next one. 4, 6, 4 stays the same. 5, 5. 4 times 4 plus 6, 22 divided by 2, 11. Okay. Next one, white one. 5, yeah, goes a line. 5, 11, 5. 5 plus 11. I think they just stay the same here. Right, because 25 plus 11, 36 divided by 6 is 6. And then from here, I think they'll just go backwards sort of. So now this is 4, 6, 4, and those will go back to 2, 2, 2, and well, eventually, they will go back all the way here. Okay, I think I ended up not making a mistake, but does this make sense? So
Yes.
at least in this case, with those starting numbers, at least this was periodic, and you can check that if you just plug in instead of numbers, you could start, with variables, x, y, z, w, t, u. Do the cycle, you can check that you will come back. And why don't we make it your homework exercise? Because I need to assign something. I don't know. So that's a reasonable thing to try. So exercise for homework. Check that this is periodic. Yes? Okay. So just not just work for 1, 1, 1, 1, but for any variables. You can use computer if you want. Okay. So this one works, but then there are, of course, other ones which don't work. So I have an example here of one which doesn't work, but I'll just show you the example. You probably don't have to compute it. So Here's a very similar one here. Let's take this quiver. White. This is black. Everybody can see it. There's double arrows this way, double arrows this way. So this is a recurrent quiver. You can check that if you mutated two white vertices, you get back the same quiver. If you mutated two black vertices, you get back the same quiver. But if you start putting numbers here, like if you try to see where it goes, they just keep growing. It will never come back. It's not periodic. So not periodic. Okay, so let's ask in this setting the same question we asked last time. Which ones are periodic and can we prove that they are periodic? So, and just like last time, actually the second part is kind of older than the first one. So this is some kind of generalization of the Zamolodchikov conjecture, which was conjecture just 2 years after his conjecture. So let me tell you what is a generalization. Here's one way to build those periodic bipartite T systems. It's called tensor product construction. So if you start with two bipartite graphs, G and H, you can create graph G tensor H. And this is just something kind of like graph theoretic. It's like, I'll draw a picture for you. Hopefully it will be clear. So here's my H. Here's my G. And basically, for each pair of vertices, one from G and one for H, I create a vertex in G times H, right? So I will try to draw it like this. So this will be one copy of H. This will be another copy of H. And this will be another copy of H. And then, of course, I will connect things which correspond to the same thing in H, and I connect things which correspond to the same thing in G. Okay, so if this is my H and this is my G, this would be my H tensor G. I didn't write a formal definition, but hopefully, does it make sense? So the vertices would be like pairs GH, where G is in G, H is in H, and then the edges would come either from edges here or from edges there. Right?
Excuse me. Can I ask you to show what will be the result of H squared then? Well, H tensor H.
H tensor H.
Yeah, to make it.
Try. Okay, I can try to draw H tensor H. So, yeah, okay. How about I take a slightly smaller H? How about this will be my H?
Yes, that will be good.
Okay, so let me try. So this will be okay, so I will create this. And there's one more for this one. And then I do One. Right, so it would have slices which look like this guy. And slices which look like the other guy. Okay. I don't know if you can you guys see my colors? I just realized that maybe you cannot really see my
Yeah,
colors.
yeah, we can see.
Like better like this.
Yes, that's better.
Okay, let's try.
Yeah.
Thank you.
Okay, I can just try to make that better. Kind of. Okay, so that's how you create the graph. And then the rule for, like, we want to actually create a quiver. So the rule for the quiver, there's a formal rule which says, like, you color your graph here black and white vertices, and you color your graph here black and white vertices. And then you create some kind of formal rule how you are, like, if this vertex used to be white here and black here, and this one, like there's some rule like that, but informally you just put arrows, so there's lots of little oriented squares. Okay, that's the rule. So here you will do something like this. You just start putting them. There's lots and lots of little oriented squares. And you can do it here too. Keep going. Okay, so that's the tensor product construction. And just like I did in this example, what we actually really, what original conjecture was about is the following. You start with two Dynkin diagrams, the same guys we introduced last time, right? ADE Dynkin diagram. For example, this one is actually D5 and this one is A3. And those two are D4 and D4. You take that tensor product. The first statement is that this will be recurrent quiver in the sense we just talked about. That if you, like, so if you color it black and white, which is still, it's a bipartite graph, so you can color it black and white. And you start clicking black, white, every time you get back the same quiver, except, up to global reversal of arrows. So it's a recurrent quiver. You can try it. I mean, the one we had before was just, this guy over here was just A2 times A3. Right, so this was a special case, but you can try and you can see that those are recurrent. But moreover, the conjecture, for a long time, it was open conjecture that this is periodic. So the conjecture, which is more general than Zamolodchikov conjecture. Right, so Zamolodchikov conjecture is the special case of it when you take one of the Dynkin diagrams, tensor with A1. If you think about it, what does it mean to tensor with A1? It just means that you take one copy of your Dynkin diagram. So that's the original Zamolodchikov thing. But this is a more general, much more general conjecture that if you take tensor product of any two Dynkin diagrams, and you start this dynamics bipartite system, black, white, black, white. So the conjecture was that it's periodic. So people conjecture that in 1993, kind of after staring at Zamolodchikov conjecture for a while. So they conjectured in 93. and it stayed open for much longer. This generality stayed open for much longer. It was proved, so let me see. The case of A times A, kind of like this. Just, it looks like a rectangle, like a square grid rectangle, right? So A tensor A. This was proved by Volkov in 2005. And I will show you this argument tomorrow. Well, not tomorrow, next time. So I will show you sort of modern formulation of his argument. It's a very pretty argument, but it only works in this case. It doesn't work. You cannot do A times D, D times E, like only works for A times A.
It is like A times A for every, like AN times AK?
That's right.
Or
so he proved AN times AM. That's right. So he solved it for this case in 2005. And then basically the general case was solved by Keller. So general case of this conjectures, by this I mean any AD Dinking diagram tensor with any AD Dinking diagram. It was Keller, or Keller actually. It was 2013. So 20 years after the conjecture was formulated. And he solved it using cluster categories. So last time I emailed you guys, or Andrei forwarded, to use some kind of introduction, actually, Keller wrote on cluster categories. So using this science, you can find this paper. I can send it to you if you want. So he proved that the periodicity in general. So for this guy, for that guy, I mean, for any Dinkin times Dinkin. Okay, so far so good.
yeah, actually, is this statement of the theorem that it's like if and only if?
I'm about to talk about it. So for a long time, until basically my courser, Zaza Pasha, and I started thinking about it like 7 years ago, nobody cared if it's if and only if. Okay, so nobody really asked this question. Just people wanted to prove that it works for Dinkin times Dinkin. Nobody asked, are there any other cases where it works? And turns out that yes, there are other cases where it works. So let me show you. So here's the simplest other case. I mean, I don't know if it's the simplest, but here's, oh, maybe it is the simplest. So here's a recurrent quiver, exactly of the kind we've been talking about. Yeah. Um, oh my notes. Way, this 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 way. Okay, that's it. That's a quiver. It's pretty small. It's recurrent. So I don't know. It's not hard to convince yourself it's recurrent. So think what happens. First of all, if you mutated all the black ones, it will create two arrows going this way, and then it will create two arrows going back. They will cancel out. Nothing happened. Right? If you mutated the white ones, slightly more complicated, like this one will create this arrow, but this one will create this arrow. They will cancel out. And you can check everything cancels out again. So you can check pretty easily that this is recurrent quiver in our sense, that if you mutate all black, stays the same. If you mutate all white, stays the same. Here's another thing you can check. I mean, it could be another exercise, like if you want. So I don't know. Let's do it. I mean, I need to come up with some exercises for you. So check that it's periodic, just like the other one. if you put any variables and you start doing black, white, you can check that pretty soon you will come back to where you started with. I mean, you can check it with first with numbers too, if you want. So I would check it with numbers for you, but I'm trying to sort of save time. So does it make sense? I'm just saying that if we did this check, we would see that this one is also periodic. You come back. But this one
Yes,
is
that
not
makes
a
sense.
tensor product. I sort of like, if you think a little bit about it, this is not of the form that G tensor H for any G and H. It's just not. You can try to convince yourself. And so what's happening here? Why? So it turns out there is more than just tensor products. Can we say which ones they are? And the answer turns out to be, in some sense, the same, almost the same as before. Here's one way to say the answer. The theorem, due to, I don't know, two pashas, is that it's periodic if and only if there exists subadditive labeling. Except I need to tell you what now subadditive labeling means. Okay, I hope you remember subadditive labeling from last time, right? So it's just put numbers at vertices, twice the number at each vertex should be bigger than the sum of neighbors. Yes, this was, you had exercise, maybe you tried to do it. So maybe you remember this. So what would it mean subadditive labeling here? Well, now we have actual directed graph. We have quiver. So we have two kinds of neighbors. We have outgoing neighbors and incoming neighbors. So we will just separately require that twice the number is bigger than the sum of outgoing ones, and that it's bigger than the sum of incoming ones. And that's it. So our definition of subadditive will be almost the same as before, that twice value at vertex V should be bigger than sum over all neighbors outgoing from V, f of u. And it should also be bigger than the sum of all neighbors incoming into V, f of u. Okay, does this make sense? So for example, over here, let's put those numbers over here. I claim it's a subadditive labeling. Why? Twice this number, 2.2, is bigger than 1 plus 1. And it's also bigger than the other 1 plus 1. Also, twice 1, 2, is bigger than 1 plus 1. And it's also bigger than the other 1 plus 1. Okay. Does the definition make sense?
Yes.
Okay. So that's the definition, subadditive labeling. Turns out the theory is essentially the same, but now, of course, the question is, well, what are those things? Which graphs do have subadditive labeling? So here's a trick we need to do. So I'm starting to run out of time. So here's the trick we need to do. Let's do the following. Let's take our quiver and color all edges which go from black to white. Let's color them red. So black to white, color red. And white to black, let's color them blue. For some reason, I don't have blue, so I'll use purple. Okay, so what will happen in this case? Red, red, red. I hope you can see. Red, blue, 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 and blue. Now, if you think about this condition, if you think about this slightly more general definition of subadditive labeling, you will realize that what it tells you is that the blue connected components and the red connected components have subadditive labeling in the old sense, which means they must be ADE Dynkin diagrams. So any quiver like this must be built somehow out of, look, this is A3, this is A3, this is A3, this is A3. And in fact, if our thing was a tensor product, yeah, let's take some simple tensor product. If our thing was a tensor product, like, right, this is A3 times A3. And if we applied what I just said, color the edges black to white red, white to black blue, what we will get? Red, 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 red. And then we will get blue, 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 blue. So you see, it falls back apart into what you started with. If you have tensor product, it's very easy to see what it is tensor product of, right? It just decomposes back into. But there are some other guys which are not tensor products, but which nevertheless are kind of connected in some more tricky way, but they still work. They still are connected just right to be a recurrent quiver and to have a subadditive labeling, and they work and they give you the periodic T system. Okay, let me stop. Any questions so far? So I'm going to tell you more. I'm going to tell you how to classify them, etc. But any questions? So
yeah, I have a question. Actually, maybe aren't they built like by a sequence of tensor products? Like we start doing tensor products on.
Be built even by a sequence of tensor products. I mean, you can try. I mean, if you can show me how to build this, but I don't think this guy is just not a tensor product at all. I mean, if you're a sequence of tensor product, you would be in particular a tensor product. But I don't think this guy is just a tensor product at all. The one on the left. He's
Okay.
just. I mean, you should try. I mean, maybe I'm wrong, but I think if you play with it, you will see that he's just not. And I could draw for you. I mean, I have much more complicated picture. Like here, oh wait, my camera is here. I'll show you. I don't have time. I was going to draw this picture for you, but like this is how more complicated guys look like. So, like, yeah, okay. So, any I will tell you more about. But ask me something now. If you, I mean, this was a good question. Any other question?
So is this criterion can be shown using some fixed point argument as well?
That's right. So the way this is proved is that basically you use a tropical version of T-system. I don't know if Sylvester told you what is tropical version.
Yeah, we talked a bit
Yeah.
about
So
this.
you use tropical version of T-system to create a fixed point, and then out of fixed point you create a subadditive label. That's right. And it's still so, and this would still just, so once you know that it must have subadditive labeling, there's still remaining question is, well, which graphs are they? Which graphs do have such subadditive labeling? And I will tell you in a second what they are. And then even for those, so far it was just one direction. So even for those, why does each of them actually give you periodic to system? Remember, it was open for 20 years that just tensor products are periodic. And this is something more general. So why are those guys periodic? So, but it turned out that once you know that tensor products are periodic, we could prove that all of those. So right now in our paper, we actually prove if and only if results. So we can classify those things and we can prove that the thing is periodic if and only if it's one of them, and we can list them. But but don't worry. I mean, there are still many open questions. I'm just sort of, but any questions? So I'm going to start telling you what those graphs are. Any questions? So the logic is like this. The answer, so which of those are periodic? Still the same as last time. They're the ones which have subadditive labeling. So you just need the slightly more general definition of subadditive labeling. And this definition basically tells you that if you color the edges in two colors, then the red components and the blue components, each of them have to be AD Dynkin diagrams. So you are somehow asking how somehow to connect to each other those, Dynkin diagrams so they would form correct graphs. And one such way to do it is tensor products, but there are apparently other ones. So what are those other ones? Okay. We have like 5 minutes. I will take 5 minutes and then I will let you go. Okay. So, and by the way, the third homework exercise, not super hard, proves that tensor products have subadditive labeling. Right. So I just said that to be periodic, you must have subadditive labeling. And I just said that it was, of course, conjecture for a long time that tensor products of Dynkin diagrams have subadditive labeling. Are periodic. So it must be the case that tensor products of Dynkin diagrams have subadditive labelings. To prove tensor products of ADE graphs have subadditive labelings.
But we can use our result from first homework,
you can
right?
use your previous results.
Okay.
Yeah, as I said, actually, it's like if you find the trick, it's not very hard. Okay. So now let me tell you how can we even find those, like classify such graphs? So turned out that in some sense we got lucky. Somebody did it for us before us for a completely different question. So here's the way to think about it. Let's think about, and it goes back to the question somebody was asking me, how to think about recurrent quivers. Let's think about adjacency matrix of this graph. Does adjacency matrix make sense? Right, so we have rows and columns labeled by vertices, and we put like 1 if there is an edge connecting them or something like that.
It's like you put in 1 minus 1 degree in the diagonal, or
no,
or just 1, 0.
Like this is vertex X, like you have here vertices X, Y, Z, W, and you have here X, Y, Z, W. And then there is edge from X to Z, so you would put like 1 over here because there is edge from X to Z.
Okay.
Something like that. So something very simple. It's just matrix which encodes edges of this graph. But let's take actually 2 separate matrices. One for red edges, one for blue edges. Right? So there's a red graph and there is a blue graph. They're not connected in general, but that's okay. Let's just take red graph, blue graph. For each of them, let's write down adjacency matrix. we can say two things about those. So first of all, red graph is built of ADEs and blue graph is built of ADEs. Such matrices are called Cartan matrices. So a matrix, adjacency matrix of a ADE graph, or like several of them like connected components, people would call it a Cartan matrix. So we are looking at a pair of Cartan matrices. And those are very special matrices. People study them in Lie algebras, etc. They basically encode for you your Lie algebra or whatever. A pair of Cartan matrices. And the fact that this quiver is recurrent, that you remember that if you mutate black, white is the same as you black, you get the same white, you mutate white. It just means what? It means that for any two vertices, the number of paths which are kind of blue-red is the same as number of paths which are red-blue, and the other way around. It just means that those two matrices commute. It just means that if you multiply them in one order or the other order, you get the same product. So we are looking for pairs of Cartan matrices of finite type which commute. Turned out that there is a person who already classified such pairs. So his name is John Stambridge. He was studying completely different questions, something in representation theory, but he had an answer. There are 5 infinite families and there are like 8 exceptional cases. One of the infinite families is tensor products, just like we know it should be. Another one is called twists. This is the example of a twist, the one I showed you over there. There is several more infinite families. There are some exceptional cases. Exceptional cases can look quite crazy. They can be quite big and kind of like impressive. Like I think Sylvester is going to show you this classification, so you will see. So turns out that such things are already classified. So when we were doing this, it was already known in some sense. We realized that somebody already did it for us. Somebody already answered for us which quivers like this have subadditive labelings. Right? So, and then the remaining part was just to prove that all of them actually work, that all of them actually do give periodic T systems. Okay, and that was just technical. Let's just not go into this. So, okay, so I should let you go, guys. But so remember, there are 3 exercises. And next time I will start talking about things we don't know. So this paper sounds like we know everything, right? We proved that it's if and only if statement. We can prove it. So, but what will be one thing I'll start talking about next time? Remember, I asked you about weakly subadditive labelings. They correspond to some other graph called affine Dynkin diagrams. And you could ask, what are some properties of those T systems associated to those? And then I will tell you what the properties are, but then it's open questions that they actually have them. So anyway, so analogs of the Zamolodchikov conjecture are still widely open in those more general worlds. Sort of that's I guess where I'm heading. So next time I'll talk about that, but in between then try to do the exercises I told you about today. I hope you're enjoying it so far. Those are pretty pictures. When you look at this classification by Stambridge, those pictures will be pretty. I hope you enjoy them. But we ran out of time. I don't think we have time for questions, but maybe somebody has some quick question. Any quick question?
Yeah. Could you maybe send us the paper, your paper about the
Yes, I will send you my paper. I will send you probably Stambridge's paper. It's a bit technical how he does it, but it's not super hard. He just talks about those graphs. He talks about eigenvalues of those matrices associated with graphs. He talks about something called Coxeter number, which is not that fancy. Sylvester can explain it to you. So anyway, it's not super hard. It's just technical proof, but in his paper. But at the end, he gets this beautiful classification. So I'll send you my paper. I'll send you Stambridge's paper. I'll think maybe I can send you something else, or we can wait till next time. Thank you for coming. See you next time.